Hello there and welcome to the Twilight Archive, where quiet curiosity meets the deep mysteries of our planet's past, and we take our time with the questions that keep scientists awake at night. I'm your narrator, and tonight we're going to explore something that happened long before recorded history, before the first cities, before agriculture, before humans even knew they were human in the way we understand it today. We're going back 42,000 years to witness one of the most remarkable events in Earth's recent geological history. An event so profound that it fundamentally changed the conditions for life on our planet, yet one that most people have never heard of. You might be wondering what could possibly have happened that long ago that would still matter today. After all, 42,000 years is a span of time that dwarfs all of human civilization. But here's the thing about Earth, and here's something that makes our planet so fascinating to study: it's not just a static ball of rock floating through space. Our planet is dynamic, alive in ways that extend far beyond the biology we see on its surface. Earth generates forces, fields, and phenomena that reach out into space itself, creating an invisible architecture that makes life as we know it possible. Imagine for a moment that you could step outside of time and observe our planet from a distance, watching it not for seconds or minutes, but across millennia. You'd see the slow dance of continents, the rise and fall of ice ages, the evolution of life forms. But there's something else you'd notice, something invisible to the naked eye but absolutely crucial to everything happening on the surface. You'd see Earth surrounded by a vast, shimmering bubble of magnetic energy, extending tens of thousands of miles into space. This is our planet's magnetic field, and it's been our silent guardian for billions of years. Most of us go through our entire lives without giving much thought to this invisible shield. We wake up, go about our business, and sleep under stars whose light has traveled across the vacuum of space to reach us, never realizing that we're protected by something we can't see, can't touch, and can barely comprehend. But 42,000 years ago, something extraordinary happened to this protective bubble. Something that would change everything. The magnetic field that had faithfully protected Earth for countless eons began to weaken dramatically. Not gradually, not over millions of years as you might expect from geological processes, but relatively quickly in geological terms. And then, in what scientists now call the Laschamp Excursion, something even more remarkable occurred: the magnetic field didn't just weaken. It began to flip. North became south, south became north, and for a period of time, Earth's magnetic compass spun wildly, leaving our planet essentially defenseless against the cosmos. Now, you might be thinking that this sounds like science fiction, like the kind of catastrophic event that belongs in a disaster movie rather than Earth's actual history. But this isn't speculation or theory. This is documented fact, written in the rocks, preserved in ancient trees, and confirmed by laboratories around the world. The evidence is so compelling, so consistent across different types of geological records, that there's no doubt it happened. The only questions that remain are about the precise details of how it unfolded and what exactly it meant for life on Earth. What makes this event so fascinating, and why we're spending time with it tonight, is that it offers us a window into something we rarely get to contemplate: what happens when one of Earth's fundamental systems fails. We live in an age where we worry about climate change, about asteroid impacts, about various threats to our technological civilization. But the Laschamp Excursion reminds us that Earth itself can undergo changes so profound that they alter the basic conditions for life across the entire planet. The story of how scientists discovered this event is almost as remarkable as the event itself. It began with trees, ancient kauri trees buried in New Zealand swamps, their massive trunks preserved for tens of thousands of years like natural time capsules. It continued with French researchers studying volcanic rocks in a remote valley, noticing something odd about the magnetic orientation of minerals that should have been straightforward to interpret. And it culminated with a growing understanding that our planet's history includes episodes of magnetic chaos that we're only now beginning to appreciate. As we journey through this story together tonight, we'll explore not just what happened 42,000 years ago, but what it means for us today. Because here's something remarkable: Earth's magnetic field is weakening again. Not as dramatically as it did during the Laschamp Excursion, at least not yet, but measurably, consistently, in ways that scientists are carefully monitoring. The magnetic North Pole is racing across the Arctic at speeds that would have been unthinkable just decades ago. Are we heading toward another magnetic reversal? And if so, what would that mean for our technology-dependent civilization? But we're getting ahead of ourselves. Before we can understand what it means when Earth's magnetic shield fails, we need to appreciate what this invisible guardian does for us every day. We need to understand the delicate balance that allows life to flourish on our planet, and why the magnetic field is so much more than just a compass needle pointing north. The Laschamp Excursion isn't just a story about the past. It's a story about resilience, about the dynamic forces that shape our world, and about the remarkable planet we call home. It's a story that begins in the core of the Earth, extends into the far reaches of space, and touches every living thing that has ever existed on our planet's surface. So settle in, and let's begin this journey together. We're going to explore one of the most extraordinary events in recent Earth history, an event that reminds us that our planet is far more dynamic and mysterious than we often realize. The shield fell silent 42,000 years ago, and the story of what happened next is one that connects geology with biology, connects the deep past with our present moment, and connects us with the cosmic forces that continue to shape our world. Right now, as you're listening to this, something extraordinary is happening around you. Something so fundamental to your existence that you've probably never given it a second thought. We're surrounded by an invisible force field, a magnetic bubble that extends tens of thousands of kilometers into space, quietly doing the work that makes life on Earth possible. Most of us learn about Earth's magnetic field in school as the thing that makes compass needles point north. We might remember something about magnetic poles, maybe even that they're not quite aligned with the geographic poles. But that simple description barely scratches the surface of what's actually going on. Earth's magnetic field isn't just a navigation tool. It's a planetary defense system. Imagine for a moment that you could see magnetic fields the way you see light. If you could, Earth would appear wrapped in an enormous, shimmering cocoon, constantly shifting and pulsing as it interacts with forces streaming from the sun. This cocoon, called the magnetosphere, begins deep inside our planet and extends far beyond the moon's orbit. It's generated by something that sounds almost like science fiction but is entirely real, a churning ocean of molten iron in Earth's outer core, spinning and convecting in patterns so complex that we're still working to understand them. The physics here are both elegant and mind-bending. As this liquid iron moves, it carries electric charges with it. And when electric charges move, they create magnetic fields. It's the same principle that powers the generators that light your house, but scaled up to planetary proportions. We call it the geodynamo, and it's been running continuously for billions of years, powered by the heat left over from Earth's formation and the decay of radioactive elements deep in the core. But here's where things get interesting, and here's why we need to understand this invisible guardian before we can grasp what happened 42,000 years ago. Earth's magnetic field doesn't just sit there. It's constantly being battered by something called the solar wind. The solar wind isn't wind in any sense we'd recognize. It's a stream of charged particles, mostly protons and electrons, flowing away from the sun at speeds of several hundred kilometers per second. Every second, the sun loses about 1 million tons of material in this solar wind, and it's been doing this for billions of years. Without Earth's magnetic field, this stream of particles would hit our atmosphere directly. You might think, what's the big deal? These are just tiny particles, after all. But here's what makes them dangerous: they're moving incredibly fast, and they carry energy. When fast-moving charged particles hit atmospheric molecules, they can knock electrons loose, creating what we call ionization. Do this enough, and you start breaking down the chemical bonds that hold our atmosphere together. We don't have to imagine what this looks like. We can see it happening to Mars right now. Mars once had a substantial atmosphere, probably thick enough to support liquid water on its surface. But Mars lacks a strong magnetic field, and over billions of years, the solar wind has been steadily stripping that atmosphere away. Today, the Martian atmosphere is less than 1% as thick as Earth's. The red planet is a cautionary tale written in geology and atmospheric chemistry. Earth's magnetic field prevents this fate by doing something remarkable. When the solar wind encounters our magnetosphere, it gets deflected around us. Picture a river flowing around a boulder, and you'll have a rough idea of what's happening, except the river is made of charged particles moving at 400 kilometers per second, and the boulder is an invisible magnetic structure the size of a small planet. This deflection isn't perfect, though, and that's actually how we know it's working. Some solar particles do manage to spiral down along magnetic field lines toward Earth's poles. When these particles hit our upper atmosphere, they excite oxygen and nitrogen molecules, causing them to glow. We see this glow as the aurora, the northern and southern lights. Every time you see an aurora, you're watching Earth's magnetic field at work, channeling potentially harmful radiation into a light show safely high above our heads. But the solar wind is just the beginning. Space is filled with cosmic rays, high-energy particles that come from exploding stars, black holes, and other exotic cosmic phenomena. Some of these particles are moving at nearly the speed of light, carrying energies millions of times greater than anything we can create in our most powerful particle accelerators. If these cosmic rays reached Earth's surface in full force, they would make the planet uninhabitable. Once again, our magnetic field comes to the rescue. It deflects most cosmic rays before they can reach our atmosphere. The ones that do get through are usually slowed down and scattered by the time they reach us. It's like having a cosmic umbrella that's been protecting us from a radiation storm that's been going on for billions of years. There's another layer to this protection that we often overlook, the atmosphere itself. But the atmosphere can only do its job because the magnetic field keeps it from being blown away. It's a partnership between the magnetosphere and the atmosphere, with each protecting the other. The magnetic field keeps the atmosphere from being stripped away by solar wind, and the atmosphere absorbs and scatters the particles that do make it through the magnetic shield. Now, here's something that might keep you up at night if you think about it too hard. This entire protective system, this invisible fortress that makes our existence possible, depends on processes happening 3,000 kilometers beneath your feet. The geodynamo that creates our magnetic field is driven by the cooling of Earth's core, the rotation of our planet, and the complex dance of fluid motions in a sea of molten metal that we've never directly observed and probably never will. And sometimes, this system falters. The geological record tells us that Earth's magnetic field has reversed many times throughout history. North becomes south, south becomes north. During these reversals, the field doesn't just flip like a switch. It weakens, sometimes dramatically. It can become chaotic, with multiple north and south poles appearing and disappearing unpredictably. And for periods that can last hundreds or even thousands of years, our planet's magnetic shield can become a shadow of its normal strength. Most of the time, these magnetic excursions happen slowly enough that life adapts. But 42,000 years ago, something extraordinary occurred. The shield didn't just weaken gradually. It nearly vanished entirely. The shield didn't just weaken gradually. It nearly vanished entirely. But here's where our story takes an interesting turn, because the first hints that this catastrophe ever happened came from one of the most unlikely sources you could imagine. Not from satellites or sophisticated magnetic observatories, but from trees. Ancient trees, to be precise, buried deep in the swampy peat bogs of New Zealand's North Island. You might be wondering how a tree could possibly tell us about cosmic radiation from 42,000 years ago. It's a fair question, and the answer lies in one of nature's most elegant recording systems. Every year, trees add a new ring of growth, and embedded within that would are trace amounts of carbon-14, a radioactive isotope that forms when cosmic rays collide with nitrogen atoms in our atmosphere. The more cosmic radiation hitting Earth, the more carbon-14 gets produced. It's like having a cosmic ray detector that's been running continuously for millennia. The kauri trees of New Zealand are particularly remarkable timekeepers. These giants can live for over 2,000 years, and when they die and fall into oxygen-poor swamps, they don't decay the way most organic matter would. Instead, they're preserved almost perfectly, like massive wooden time capsules waiting for someone to read their story. And in the 1990s, researchers began doing exactly that. Imagine you're a scientist carefully extracting thin slices from these preserved logs, each ring representing a single year of growth. You're looking at wood that formed when mammoths still roamed the earth, when the ancestors of modern humans were spreading across continents, when the world was a very different place. But as you analyze the carbon-14 content of these rings, something unusual starts to emerge from the data. Around 42,000 years ago, according to the tree ring chronology, something dramatic happened. The carbon-14 levels don't just increase gradually, they spike sharply upward, reaching levels nearly twice as high as normal. For a scientist studying cosmic radiation, this is like finding a smoking gun. It means that for some period of time, Earth was being bombarded by cosmic rays at levels far beyond what we experience today. But one tree, however well preserved, doesn't make a global story. What made this discovery truly compelling was that similar patterns began showing up in tree ring records from around the world. Ancient oaks from German bogs, preserved pines from the Swiss Alps, fossilized wood from North American sites, all telling the same story. Roughly 42,000 years ago, our planet experienced a sustained period of dramatically increased cosmic radiation. We need to pause here and appreciate what this means. These trees were essentially acting as biological dosimeters, automatically recording radiation levels year by year, century by century. They weren't just growing in the shadow of some local cosmic event. This was planetary. Global. Something had compromised Earth's natural defenses against cosmic radiation on a scale that affected every living thing on the planet. Now, you might think that scientists would immediately leap to the conclusion that Earth's magnetic field had failed. But science doesn't work that way. The tree ring data was suggestive, even compelling, but it was just one piece of a much larger puzzle. What the researchers had found was evidence of an effect, not necessarily its cause. Cosmic radiation could spike for any number of reasons. A nearby supernova explosion. Solar storms of unprecedented magnitude. Or yes, failure of our magnetic shield. The breakthrough came when researchers started combining the tree ring data with other types of evidence. Ice cores from Greenland and Antarctica began showing unusual chemical signatures around the same time period. Marine sediments revealed changes in the production of beryllium-10, another isotope created by cosmic ray bombardment. Each new dataset added another layer of confirmation. This wasn't just a regional phenomenon recorded by a few trees. This was a global event preserved in multiple archives of Earth's history. But perhaps the most intriguing aspect of this discovery was its timing. 42,000 years ago falls right in the middle of a fascinating period in human history. It's when modern humans were spreading across Europe and Asia, when cave art was beginning to flourish, when significant changes were happening to human culture and possibly human evolution itself. Could there be a connection? We'll explore that question later, but for now, let's appreciate the remarkable detective work that brought us this far. These New Zealand kauri trees, preserved in their swampy graves, had given researchers the first solid evidence that something extraordinary had happened to our planet's cosmic radiation environment 42,000 years ago. But trees, for all their usefulness as natural archives, can only tell us so much. They could record the effect, the increased radiation, but they couldn't tell us definitively what had caused it. For that, scientists would need to turn to an entirely different kind of natural archive. Not the organic records preserved in wood and ice, but the magnetic memory locked within volcanic rocks. Because while trees record cosmic radiation, volcanic minerals record something even more fundamental, the strength and direction of Earth's magnetic field itself. This is where our story shifts from the quiet swamps of New Zealand to the volcanic landscapes of central France, where a discovery made decades earlier was about to take on profound new significance. The tree ring evidence had identified when Earth's cosmic defenses failed. Now it was time to understand how. Think about it this way: the kauri trees had essentially raised an alarm, pointing to a specific moment in Earth's history when something went terribly wrong. They'd identified the symptoms of a planetary-scale crisis. But to understand what actually happened to our magnetic shield during those crucial millennia 42,000 years ago, researchers would need to consult an archive that could preserve the magnetic field's actual behavior, not just its effects. They needed rocks that could remember the direction and strength of ancient magnetism itself. And in the volcanic deposits of a small French village, they would find exactly what they were looking for. The village of Laschamp sits quietly in the Chaîne des Pays, a line of dormant volcanoes that cuts through the French countryside like a geological spine. It's the sort of place where ancient lava flows have been softened by centuries into gentle hills, where sheep graze on what were once fields of molten rock. You might drive through Laschamp today and see nothing more than pastoral farmland. But beneath your wheels lies one of the most important geological archives on Earth. In the 1960s, French geophysicists Norbert Bonhomet and Jacques Babkine arrived here with a simple mission: to study the magnetic properties of these old volcanic rocks. They were part of a growing community of scientists who had learned to read the magnetic memory stored in cooled lava. When volcanic rock solidifies, its iron-rich minerals align themselves with Earth's magnetic field like tiny compasses, freezing that orientation in place for millions of years. It's a remarkably faithful recording system, one that preserves not just the direction of ancient magnetism, but its intensity as well. What they found in those Laschamp lava flows defied everything they thought they knew about Earth's magnetic behavior. The magnetic minerals weren't pointing north as expected. Instead, they were oriented in completely the wrong direction, as if the rocks had formed when Earth's magnetic poles were reversed. But that was just the beginning of the puzzle. As Bonhomet and Babkine collected more samples from different layers of rock, a stranger story began to emerge. These weren't just simple reversed rocks. The magnetic direction seemed to wander chaotically through the rock sequence, as if Earth's magnetic field had been stumbling around like a drunken compass needle. Some layers showed the field pointing northeast, others southeast, still others almost straight down into the Earth. The implications were staggering. Magnetic reversals were known to happen, but they were supposed to be clean transitions where north becomes south and south becomes north over thousands of years. What the Laschamp rocks were revealing looked more like complete magnetic pandemonium. And when they dated these volcanic layers using the radioactive decay of potassium into argon, they found something even more remarkable: this magnetic chaos had occurred around 42,000 years ago. Now, you might be wondering how confident we can be in these interpretations. After all, we're talking about reading magnetic signatures in rocks that are older than human civilization, using techniques that were still quite new in the 1960s. The skepticism was warranted and immediate. Could there be some local geological effect that had scrambled the magnetic signal? Could the dating be wrong? The answer came through one of science's most powerful tools: independent confirmation. Within a few years, scientists working in completely different locations began finding rocks of the same age with the same bizarre magnetic signatures. Volcanic flows in Iceland showed identical patterns of magnetic wandering. Sediment cores from the Mediterranean revealed the same chaotic field directions. Even more remarkably, studies of volcanic rocks from as far away as Hawaii and New Zealand began telling the same story. This global consistency was crucial because it ruled out local explanations. You can't have a regional effect that shows up identically on opposite sides of the planet. Whatever had happened to Earth's magnetic field 42,000 years ago, it had been a global phenomenon of extraordinary proportions. The technical term for what the Laschamp rocks revealed is a geomagnetic excursion, and it's worth pausing to understand exactly what that means. A full magnetic reversal involves the complete and permanent flip of Earth's magnetic poles, north becoming south and south becoming north. These happen roughly every few 100,000 years and represent fundamental reorganizations of the magnetic field that can take thousands of years to complete. An excursion is different, more like a magnetic seizure. The field doesn't just reverse cleanly, it weakens dramatically and begins to wander. The North Pole might migrate toward the equator, then loop back toward the South Pole, then wander somewhere else entirely. During an excursion, the magnetic field can collapse to a tiny fraction of its normal strength, sometimes dropping below 10% of typical values. What made the Laschamp discovery so significant was its timing and duration. The magnetic chaos lasted for nearly 1,000 years, from about 42,500 to 41,500 years ago. For almost a millennium, Earth's magnetic shield was not just weakened but actively dysfunctional. Instead of a stable north-south field deflecting cosmic radiation away from our planet, there was a chaotic, fluctuating maze of magnetic forces that provided almost no protection at all. The rocks told this story with remarkable precision because volcanic eruptions provide such clean snapshots of ancient magnetic conditions. Each lava flow captures the field direction at the exact moment it cooled, like pressing the shutter on a camera. By studying multiple flows from the same period, scientists could reconstruct how the magnetic field had evolved through time, creating a kind of stop-motion movie of magnetic chaos. But perhaps the most striking aspect of the Laschamp discovery was how it revealed the dynamic nature of our planet's magnetic system. We tend to think of Earth's magnetic field as a constant, as reliable as gravity or the rising sun. The Laschamp rocks showed that this fundamental feature of our planet could undergo complete breakdown and reconstruction within a human lifespan. This wasn't just an academic curiosity. As scientists began to understand what a collapsed magnetic field would mean for life on Earth, the implications became deeply unsettling. A weakened magnetosphere would allow solar particles and cosmic radiation to pour through our atmosphere in unprecedented quantities. The ozone layer would be bombarded and potentially destroyed. Climate systems could be thrown into chaos. Any creatures living on the surface 42,000 years ago would have experienced conditions unlike anything in Earth's recent history. The Laschamp discovery had opened a door into one of the most extraordinary periods in our planet's past, a time when the invisible shield that makes life possible had essentially vanished. And as we'll see, the consequences of that disappearance would ripple through Earth's climate, atmosphere, and perhaps even the story of human evolution itself. So there we were, 42,000 years ago, with Earth's magnetic field stuttering and failing like a dying engine. Picture this: the invisible dome that had protected our planet for billions of years suddenly began to collapse, leaving us essentially naked to the fury of space. Now, when we talk about Earth's magnetic field weakening to 6% of its current strength, that number might not immediately hit you with the full weight of what it means. Let me put it this way: imagine if the walls of your house suddenly became as thin as tissue paper while a hurricane raged outside. That's essentially what happened to our planet's defenses during the Laschamp excursion. The magnetic field strength we measure today averages about 50,000 nanoteslas at the surface. It's a number that means little to most of us, but it represents a protective barrier so fundamental that we've never known life without it. During the Laschamp event, this dropped to roughly 3,000 nanoteslas. The shield that had deflected the solar wind, that constant stream of charged particles flowing from the sun at over 1,000,000 miles per hour, simply wasn't strong enough anymore. And so the solar wind began to penetrate. You might wonder what this actually looked like from the ground. The most visible sign would have been the auroras. Today, we think of the northern lights as something magical confined to places like Alaska, northern Canada, and Scandinavia. They occur when solar particles, channeled by our magnetic field lines, collide with atoms in the upper atmosphere roughly 60 to 200 miles above our heads. The interaction creates those flowing curtains of green, blue, and red light that dance across polar skies. But during the Laschamp Excursion, with the magnetic field in chaos and offering little protection, auroras would have appeared as far south as the equator. Imagine standing in what is now Central Africa or the Amazon basin and looking up to see the entire sky pulsing with ethereal light. These weren't the gentle, dancing auroras we know today. These were intense, persistent displays caused by a relentless bombardment of solar particles that had nowhere else to go. The geological evidence for this comes from ice cores and marine sediments that show dramatic increases in cosmogenic isotopes, atoms created when cosmic rays slam into our atmosphere. Beryllium-10, carbon-14, chlorine-36. These isotopes are like fingerprints left by cosmic radiation, and during the Laschamp period, their concentration spiked to levels we rarely see in the geological record. Let's think about what this bombardment actually meant for the planet. When high-energy particles from space hit Earth's atmosphere, they don't just create pretty lights. They trigger cascades of secondary particles, flooding the upper atmosphere with radiation levels that would make a modern nuclear physicist nervous. Researchers estimate that cosmic ray intensity during the Laschamp excursion increased by roughly 200 to 300% compared to today. Now here's where it gets particularly interesting, and a bit unsettling. We know from careful analysis of tree rings and ice cores that this wasn't a brief cosmic hiccup. The magnetic field remained critically weakened for somewhere between 800 and 1,400 years. That's roughly 30 to 50 human generations living under a compromised shield, experiencing radiation levels and atmospheric conditions unlike anything in recorded human history. The solar particles streaming through the weakened magnetosphere didn't just create spectacular light shows. They fundamentally altered the chemistry of Earth's upper atmosphere. When cosmic rays collide with nitrogen and oxygen molecules 20 to 30 miles above the surface, they break these molecules apart, creating a cascade of chemical reactions. Some of these reactions produce nitrogen oxides, compounds that, as we'll explore shortly, would prove devastating to another crucial protective layer, our ozone. But the effects weren't confined to the upper atmosphere. The constant particle bombardment would have created electrical disturbances throughout the atmosphere. Lightning patterns likely changed. Radio wave propagation, if radios had existed, would have been chaotic and unreliable. The entire electromagnetic environment of Earth was fundamentally different. Researchers studying this period have found something else remarkable in the geological record: massive spikes in the production of radioactive isotopes that only form when cosmic rays interact with the atmosphere. These isotopes then rain down onto the surface, becoming incorporated into tree rings, ice layers, and lake sediments. It's as if the planet was being continuously dusted with the signature of cosmic bombardment. Think about the organisms living during this time. Every creature on Earth, from the smallest bacteria to the largest megafauna, was experiencing elevated levels of cosmic radiation. While life had evolved various mechanisms to cope with the normal background radiation that constantly bathes our planet, the Laschamp Excursion represented something far beyond normal. We can see evidence of this biological stress in various ways. Mutation rates in organisms would have increased. DNA damage from cosmic radiation would have been more frequent and more severe. Some researchers have even suggested that the elevated radiation during this period might have driven evolutionary changes, forcing rapid adaptations in species that survived. The most haunting aspect of all this is how alone Earth was during those 1,000 years. The magnetic field that connects us to the solar wind, that creates a kind of electromagnetic dialogue between Earth and Sun, had essentially gone silent. Our planet was no longer deflecting the solar wind around itself like a stone in a stream. Instead, the stream was washing directly over us, carrying away particles from our upper atmosphere and fundamentally altering the delicate balance that makes complex life possible. And yet, somehow, life persevered. The plants kept growing, the animals kept breathing, and somewhere in Africa and Europe, early humans continued their daily struggles for survival, probably unaware that their world was experiencing one of the most extraordinary geophysical events in recent planetary history. But the cosmic bombardment was just the beginning of Earth's troubles during the Laschamp Excursion. The particles flooding through our compromised magnetic shield were about to trigger an atmospheric catastrophe that would reshape the very air our ancestors breathed, starting with the protective ozone layer that shields us from the sun's most dangerous radiation. Now we reach the heart of what made the Laschamp Excursion so devastating for life on Earth. You see, when we talk about cosmic rays flooding through our weakened magnetic field, it's tempting to think of this as a purely space-based problem. But the real catastrophe was happening right here in our atmosphere, in a delicate layer of gas that most of us never think about but couldn't live without for a single day. The ozone layer sits roughly 25 kilometers above your head right now, a thin veil of 3 oxygen molecules that forms our planet's chemical sunscreen. Under normal circumstances, this layer does something remarkable. It absorbs the vast majority of the sun's ultraviolet B radiation, the kind that causes sunburn, skin cancer, and can literally cook organic molecules. Without ozone, life as we know it simply cannot exist on land. But during the Laschamp Excursion, this protective layer came under assault from an unexpected direction. Let's think about what happens when cosmic rays, high-energy particles from deep space, slam into our atmosphere. These aren't gentle visitors. They arrive moving at nearly the speed of light, carrying energies millions of times greater than anything we can produce in our most powerful particle accelerators. When they collide with nitrogen and oxygen molecules in the upper atmosphere, they shatter them into fragments, creating cascades of secondary particles and, crucially, producing nitrogen oxides. Now here's where the chemistry gets interesting and destructive. These nitrogen oxides, molecules like nitric oxide and nitrogen dioxide, are ozone's natural enemies. They act as catalysts in chemical reactions that break apart ozone molecules, and here's the insidious part: the nitrogen oxides aren't consumed in the process. A single molecule can destroy thousands of ozone molecules before it's finally removed from the atmosphere. It's like having a key that can unlock and destroy door after door, never wearing out. During the Laschamp Excursion, with Earth's magnetic field operating at just 6% of its normal strength, cosmic ray bombardment increased dramatically. Some estimates suggest the flux of cosmic rays reaching our atmosphere was 10 to 50 times higher than normal. All of those high-energy particles were smashing into our air, creating unprecedented amounts of nitrogen oxides, and the ozone layer began to collapse. We can see evidence of this catastrophe preserved in ice cores from Greenland and Antarctica. The chemical signature is unmistakable. Layers of ice formed 42,000 years ago contain elevated levels of nitrates, the end products of those destructive nitrogen compounds raining down from the ravaged upper atmosphere. It's as if the ice is keeping a chemical diary of the day our planet's sunscreen failed. But how severe was this ozone depletion? Modern research suggests it was far worse than anything we've experienced in recorded history. The infamous ozone hole over Antarctica, discovered in the 1980s and caused by human-made chemicals, reduced ozone levels by about 40% at its worst. During the Laschamp Excursion, ozone depletion may have reached 60 to 70% globally, with some regions seeing near-complete loss of their protective layer. Imagine stepping outside on what we'd consider a normal day, except the sun's UV radiation is suddenly 5 to 10 times more intense than the strongest tropical sunlight. That's what our ancestors faced. The effects would have been immediate and devastating. Plants, particularly those with large leaf surfaces, would have suffered massive die-offs. The base of entire food chains would have collapsed as microscopic organisms in lakes and oceans, unable to cope with the increased radiation, began to perish en masse. Trees tell us part of this story. Ancient wood from the Laschamp period shows unusual growth patterns, with some species exhibiting the kind of stress rings we normally associate with severe droughts or fires. But there's something else in those tree rings: elevated levels of carbon-14, a radioactive isotope produced when cosmic rays interact with nitrogen in the atmosphere. The trees were literally incorporating the signature of cosmic bombardment into their annual growth, recording the crisis in their cellular structure. The ozone catastrophe wasn't just a terrestrial problem. It affected the entire atmospheric system in ways we're still learning to understand. As UV radiation poured through the compromised ozone layer, it began breaking apart water vapor and other molecules in the lower atmosphere, creating unusual chemical species that don't normally exist in significant quantities. These reactive molecules then went on to trigger other atmospheric changes, creating a cascade of effects that rippled through the entire climate system. You might wonder how anything survived such an onslaught. The answer lies partly in geography and partly in the remarkable adaptability of life itself. Organisms living at high latitudes, where the sun's angle is low, experience somewhat less UV stress. Cave-dwelling creatures and those living in deep forests found refuge under natural shelters. Ocean life had the protective depth of water to shield them, though even there, the surface layers became hostile to many forms of marine life. But perhaps most remarkably, some organisms actually thrived during this period of atmospheric chaos. Deep-sea bacteria that normally live in environments already bathed in radiation found themselves better adapted than surface-dwelling life. Some researchers have suggested that the Laschamp Excursion may have been one of the evolutionary pressures that drove certain species to develop more sophisticated DNA repair mechanisms, genetic innovations that persist in their descendants today. The recovery of the ozone layer was tied directly to the recovery of Earth's magnetic field. As the magnetic shield slowly regained its strength over the course of several centuries, cosmic ray bombardment decreased, nitrogen oxide production dropped, and the ozone layer began to rebuild itself. But this wasn't a quick process. Atmospheric modeling suggests it may have taken several hundred years for ozone levels to return to anything approaching normal, meaning multiple generations of our ancestors lived under skies that offered little protection from the sun's most dangerous radiation. This ozone catastrophe helps explain some of the mysterious patterns we see in the archaeological and fossil records from 42,000 years ago. The timing isn't coincidental. When we look ahead to examine the broader climate impacts of the Laschamp Excursion, we'll see how this atmospheric crisis contributed to a cascade of environmental changes that reshaped continents and may have influenced the very course of human evolution. Now we come to one of the most intriguing puzzles in the entire Laschamp story. While our ancestors looked up at auroras dancing across equatorial skies and felt the sting of intensified ultraviolet radiation, the Earth itself was undergoing dramatic transformations that reached far beyond the atmosphere. Ice sheets began expanding across northern continents. Deserts crept into regions that had been green. Ocean currents shifted their ancient patterns. The question that keeps researchers awake at night is this: did the collapse of our magnetic shield directly cause these massive climate changes, or did we simply witness the most extraordinary cosmic coincidence in human prehistory? Let's start with what we know happened to the climate around 42,000 years ago. In Greenland, ice cores tell us that temperatures began dropping sharply, marking the beginning of what paleoclimatologists call Heinrich Event 4. This wasn't a gradual cooling but a relatively rapid shift that locked vast amounts of water into expanding ice sheets. The Fennoscandian ice sheet, which covered much of northern Europe, began one of its most significant growth phases. In North America, the Laurentide ice sheet pushed further south than it had in thousands of years. But ice sheets were only part of the story. Across the world's arid regions, deserts expanded dramatically. The Sahara, already substantial, grew larger and more hostile. In Australia, the continent became significantly drier, contributing to what some researchers call the late Pleistocene extinction event. Lake levels dropped across multiple continents. Even tropical regions experienced shifts in rainfall patterns that would have been devastating for the ecosystems that had adapted to more stable conditions. Now, here's where things get fascinating and frustrating in equal measure. The traditional explanation for these climate changes has nothing to do with magnetic fields. The dominant theory points to something called the Dansgaard-Oeschger cycle, a natural climate oscillation driven by changes in ocean circulation, particularly in the North Atlantic. According to this view, the expansion of ice sheets and the growth of deserts around 42,000 years ago were simply part of Earth's natural climate variability during the last ice age. But that timeline creates an uncomfortable coincidence. We have the most dramatic magnetic field collapse in hundreds of thousands of years happening at precisely the same time as one of the most significant climate shifts of the late Pleistocene. Some scientists are willing to accept this as mere chance. Others find the synchronicity too compelling to ignore. So how might a collapsing magnetic field actually influence global climate? We've already discussed how cosmic radiation destroyed ozone and allowed more ultraviolet light to reach the surface. But the effects go deeper than that. When high-energy particles from space collide with our atmosphere, they don't just create chemical reactions that damage ozone. They also seed cloud formation in ways that we're only beginning to understand. Here's the mechanism: cosmic rays create ionization in the atmosphere, producing charged particles that can act as condensation nuclei for water vapor. More cosmic rays potentially mean more cloud formation. And more clouds, depending on their altitude and type, can either warm or cool the planet. Low, thick clouds tend to cool the surface by reflecting sunlight back to space. High, thin clouds tend to warm it by trapping heat. The balance between these effects during the Laschamp Excursion could have been enough to tip regional climate systems into dramatically different states. There's another pathway that researchers are exploring. The flood of solar particles that penetrated Earth's weakened magnetosphere didn't just affect the atmosphere chemically. It also influenced atmospheric electricity and may have altered global weather patterns through mechanisms we don't yet fully comprehend. Some studies suggest that changes in atmospheric ionization can affect the formation of storm systems and the behavior of jet streams. But proving causation rather than correlation requires incredibly careful detective work. Scientists have been comparing the timing of magnetic field changes with climate records from around the world, looking for patterns that might support or refute a direct connection. The results are mixed and often depend on how precisely you can date both the magnetic and climate events in different locations. In 2021, a team led by researchers at the University of New South Wales published what they called the first comprehensive climate modeling study of the Laschamp Excursion. They fed data about the weakened magnetic field into sophisticated computer models that simulate global climate systems. The results were striking. Their models predicted many of the climate changes that actually occurred, including the expansion of ice sheets and the drying of Australia. Yet other researchers remain skeptical. They point out that climate models are imperfect tools, especially when trying to simulate conditions so different from today's. They also note that the climate changes of 42,000 years ago fit well within the range of natural variability we see throughout the Ice Age record. The burden of proof, they argue, remains on those claiming that magnetic field changes can drive major climate shifts. What we can say with confidence is that the Laschamp Excursion occurred during a period of remarkable environmental instability. Whether the magnetic collapse was a cause, an effect, or simply a concurrent event, it happened at a time when Earth's climate system was already under stress. The weakened magnetosphere may have been the final push that tipped various regional climates into new configurations, or it may have simply been another stressor added to an already complex mix of changing orbital cycles, ocean currents, and atmospheric composition. The debate continues in part because the stakes are so high for understanding our own future. If magnetic field changes can indeed influence global climate, then the current weakening of Earth's magnetic field takes on additional significance beyond its effects on technology and satellite communications. We need to understand these connections not just to satisfy our curiosity about the past, but to better predict what might be coming. As we piece together this ancient climate puzzle, we're also uncovering evidence that the Laschamp Excursion coincided with dramatic changes in human populations and behavior. The expansion of deserts and ice sheets wouldn't have gone unnoticed by our ancestors, and their responses to these environmental challenges may have shaped the very trajectory of human evolution. Here's something remarkable that keeps archaeologists and geneticists awake at night. The Laschamp Excursion, with its 1,000 years of magnetic chaos, aligns almost perfectly with one of the most significant transitions in human history. Around 42,000 years ago, as Earth's magnetic shield faltered and cosmic radiation flooded our atmosphere, Neanderthals were entering their final chapter. And modern humans? We were just beginning to leave behind some of the most stunning artistic achievements our species has ever created. You might be wondering if this timing is just coincidence. After all, correlation isn't causation, as we're constantly reminded in science. But when you start examining the evidence more closely, the connections become harder to dismiss. The Neanderthals, who had survived ice ages and climate shifts for hundreds of thousands of years, began their final decline right around the time our planet lost its magnetic protection. Meanwhile, early modern humans were spreading across Europe and leaving behind cave paintings that, in some cases, seemed to capture the very cosmic light shows that the weakened magnetosphere would have created. Let's start with what we know about Neanderthal populations during this period. Genetic studies of Neanderthal remains have revealed something fascinating. Their populations experienced severe bottlenecks around 40,000 to 42,000 years ago. These weren't gradual declines but sharp contractions in population size, exactly what you'd expect from environmental stress. We're talking about groups that had successfully adapted to harsh conditions for millennia suddenly finding themselves struggling to maintain viable breeding populations. Now, traditional explanations for Neanderthal extinction have focused on competition with modern humans, climate change, and disease. All valid factors, certainly. But the Laschamp Excursion adds another layer to consider. Think about what 1,000 years of weakened magnetic protection would have meant for any population trying to survive outdoors. Increased UV radiation from the damaged ozone layer. Disrupted weather patterns. Possibly even direct radiation exposure during the most intense periods of cosmic bombardment. Neanderthals, with their robust build and cold-adapted physiology, were specialists. They had evolved over hundreds of thousands of years to thrive in specific environmental conditions. When the Laschamp Excursion began reshaping those conditions, potentially quite rapidly in geological terms, their specializations might have become liabilities rather than advantages. But here's where the story gets truly intriguing. While Neanderthal populations were contracting, modern humans were doing something unprecedented. They were creating art. Not just any art, but some of the most sophisticated cave paintings ever discovered. The caves at Lascaux, Altamira, Chauvet, these masterpieces date to roughly the same period as the Laschamp Excursion. Coincidence? Maybe. But consider what the night sky would have looked like to our ancestors during this time. With Earth's magnetic field operating at just 6% of its normal strength, auroras would have been visible much farther from the poles than they are today. Instead of being confined to the Arctic and Antarctic regions, these dancing curtains of light would have appeared across temperate latitudes. Imagine being an early human in what is now France or Spain, looking up to see brilliant green and red lights rippling across the sky night after night. Colors that had no precedent in your daily experience, movements that seemed almost alive. Some researchers have proposed that certain cave paintings might actually represent these auroral displays. The abstract patterns, the flowing forms, the unusual color choices, they begin to make sense when you consider that the artists might have been documenting spectacular natural light shows that we can barely imagine today. Of course, we can't prove this connection definitively. Cave art is notoriously difficult to interpret, and ancient humans had plenty of other inspiration for abstract forms. But the timing is suggestive. There's another angle to consider here, one that touches on the very nature of human consciousness and creativity. Some anthropologists have argued that the period around 40,000 years ago represents a cognitive revolution, the emergence of fully modern human behavior including symbolic thought, complex language, and artistic expression. What if this cognitive leap wasn't just an internal development but partly a response to external pressures? The environmental chaos of the Laschamp Excursion would have demanded new kinds of adaptation. Groups that could innovate, communicate complex information, and maintain social cohesion across challenging conditions would have had significant advantages. Perhaps the same cosmic forces that may have stressed Neanderthal populations to breaking point actually accelerated the development of modern human capabilities. This isn't to suggest that cosmic radiation directly rewired human brains. Evolution doesn't work that way. But environmental pressure has always been a driver of innovation, and the Laschamp Excursion created pressures unlike anything our species had previously encountered. Groups that developed better tools, more flexible social structures, and more effective communication, including symbolic representation through art, would have been better equipped to navigate an unstable world. Genetic evidence supports some version of this story. DNA studies show that modern human populations outside Africa experienced significant bottlenecks around this same time period, but unlike Neanderthals, we recovered and expanded. Our species demonstrated a resilience that allowed us not just to survive the cosmic chaos but to emerge from it with new capabilities. The cave art angle becomes even more intriguing when you consider that many of the most famous painted caves show evidence of repeated visits over thousands of years. These weren't one-time artistic expressions but ongoing cultural centers, places where knowledge was preserved and transmitted across generations. If some of these paintings do represent auroral displays from the Laschamp period, they might be humanity's first attempts to document and understand cosmic phenomena. Of course, we need to be careful not to oversimplify what was certainly a complex set of interactions. The relationship between cosmic events, environmental change, and human evolution is anything but straightforward. Climate shifts, population pressures, technological innovations, and genetic factors all played roles in shaping this critical period in our species' development. But as we continue mapping the genetic and archaeological evidence from this era, the Laschamp Excursion keeps appearing as a significant piece of the puzzle. Whether it was a primary driver of change or simply an additional stress on already evolving populations, it clearly coincided with transformative moments in human history. And perhaps that cosmic light show our ancestors might have witnessed serves as a reminder that we've always been part of something much larger than ourselves. Whether it was a primary driver of change or simply an additional stress on already evolving populations, it clearly coincided with transformative moments in human history. And perhaps that cosmic light show our ancestors might have witnessed serves as a reminder that we've always been part of something much larger than ourselves. But here's something remarkable about the Laschamp Excursion that we haven't fully explored yet. While our human ancestors could only witness the event as it unfolded, we have something they didn't: the ability to read the permanent record left behind in stone and sediment. You might be wondering how we can be so confident about something that happened 42,000 years ago, when written human history goes back barely a few thousand years. The answer lies in the fact that Earth itself has been keeping meticulous records all along. Imagine you're holding a volcanic rock that formed during the Laschamp Excursion. When that rock was molten lava, tiny iron-rich minerals within it acted like microscopic compass needles, aligning themselves with Earth's magnetic field as the rock cooled and hardened. Once solid, those magnetic minerals became frozen in time, preserving the exact direction and intensity of the magnetic field at that moment. It's like having a snapshot of the planet's magnetic state from tens of thousands of years ago, captured in stone. This is how Bernard Brunches first discovered magnetic reversals in 1906, studying lava flows in the French countryside. He found rocks where the magnetic minerals pointed south instead of north, opposite to what they should. At first, many scientists dismissed his findings. The idea that Earth's magnetic field could completely flip seemed too extraordinary to believe. But as more evidence accumulated from volcanic rocks around the world, the reality of magnetic reversals became undeniable. The Laschamp Excursion shows up everywhere we look, once we know how to read the signs. In volcanic sequences from Iceland to Hawaii, the same magnetic chaos is recorded. The iron-rich minerals in these rocks tell us that the magnetic field wasn't just weak during this period, it was genuinely confused. In some locations, the magnetic signature shows the field pointing in completely different directions from one lava flow to the next, sometimes separated by only decades or centuries. But volcanic rocks aren't the only witnesses to this ancient magnetic turmoil. We find the signature preserved in sediments from lake beds, where tiny magnetic particles settled layer by layer, year after year. As these particles drifted down through the water column, they aligned with the magnetic field just like those minerals in cooling lava. When buried and compressed into sedimentary rock, they preserved that orientation for millennia. Some of the most compelling evidence comes from unexpected places. Coral reefs in the Pacific, for instance, incorporate magnetic minerals as they grow. These ancient coral formations show the same magnetic anomalies during the Laschamp period. Deep-sea sediment cores drilled from ocean floors reveal the same story, a consistent global signature of magnetic instability exactly 42,000 years ago. Perhaps most fascinating are the records from Arctic lake beds. In places like northern Alaska and Siberia, where permafrost has preserved sediments in pristine condition, we can read the magnetic history with extraordinary precision. These sediments show not just that the field was weak and chaotic, but how it changed year by year during the excursion. The record reveals that the magnetic chaos wasn't sudden, it built up gradually over several centuries, reached a climax lasting about 500 years, then slowly recovered. What's particularly striking is how consistent this story is around the globe. When scientists compare magnetic records from Australia to those from Greenland, from Chile to Japan, they find the same basic pattern. The timing matches. The intensity changes match. The directional chaos matches. This global consistency is what gives us confidence that we're not looking at local anomalies or measurement errors, but at a genuine planetary event. The precision of these records is actually quite remarkable. By measuring the magnetic orientation of sediment layers just millimeters apart, scientists can track changes that occurred over decades. They can see periods where the magnetic field seemed to stabilize briefly before plunging back into chaos. They can identify moments where the field tried to reassert itself in its normal configuration before failing again. One particularly dramatic example comes from a volcanic sequence in the Caucasus Mountains, where a series of lava flows captured the magnetic field in the act of reversing. The oldest flow shows a normal magnetic field pointing north. The next flow, erupted perhaps a century later, shows the field tilted at a steep angle. The third flow captured the field pointing almost sideways. And the youngest flow shows a fully reversed field pointing south. It's like watching a slow-motion movie of a magnetic pole flip, preserved in stone. These geological records also help us understand something crucial about the Laschamp Excursion. It wasn't an instant catastrophe, but a drawn-out process. The magnetic field didn't simply switch off one day and switch back on 1,000 years later. Instead, it went through a complex dance of weakening, wandering, briefly reversing, partially recovering, weakening again, and finally stabilizing in its familiar configuration. This gradual progression shows up in the atmospheric records too. Those elevated levels of cosmic radiation that we discussed earlier weren't constant throughout the excursion. They peaked during the periods of greatest magnetic weakness and subsided when the field showed signs of recovery. The geological record suggests our planet went through several cycles of vulnerability and partial recovery before the magnetic shield fully returned. What's perhaps most sobering is realizing that this rock record represents just one excursion among many. As scientists have studied magnetic minerals from older and older formations, they've discovered that the Laschamp event was not unique. Earth's magnetic field has undergone similar periods of instability throughout geological history, roughly every 200,000 to 300,000 years on average. The stones beneath our feet are keeping score, maintaining a library of magnetic memory that stretches back millions of years. Each volcanic eruption, each layer of sediment, each growing coral reef adds another page to this geological record. And that record tells us something both humbling and reassuring about our planet's magnetic guardian. The geological record's reassuring consistency carries an unsettling counterpoint. Right now, as we speak, Earth's magnetic field is doing something that should make us pause and pay attention. It's weakening. This isn't speculation or distant theory. We can measure it happening. Over the past 2 centuries, the strength of Earth's magnetic field has declined by roughly 10%. That might not sound dramatic, but in geological terms, it's like watching paint dry in fast forward. The European Space Agency's Swarm satellite constellation, launched specifically to monitor our planet's magnetic behavior, sends down data that tells an increasingly clear story. Our magnetic shield isn't stable. It's restless. But here's where things get really interesting, and perhaps a little unnerving. The magnetic North Pole itself has abandoned any pretense of staying put. For most of recorded history, magnetic north wandered around the Canadian Arctic at a leisurely pace, moving maybe 10 or 15 kilometers per year. That's the kind of drift that cartographers could manage, the sort of predictable change that mariners learn to account for when calibrating their compasses. Not anymore. Since the 1990s, magnetic north has been racing across the Arctic Ocean toward Siberia at speeds that boggle the mind of anyone who thinks in geological time. We're talking about 50 kilometers per year, sometimes more. In 2001, the pole crossed into international waters. By 2019, it had traveled over 1,600 kilometers from its 1900 position. That's not drift. That's migration. You might wonder what's driving this magnetic restlessness, and that brings us back to those churning currents of molten iron deep beneath our feet. The same convective processes that create our magnetic field also make it inherently unstable. Think of it like a pot of soup simmering on a stove. Sometimes the convection patterns shift, the flow changes direction, and suddenly your magnetic North Pole is sprinting toward Siberia faster than a migrating caribou. Scientists studying this phenomenon have coined a term that sounds almost poetic: magnetic jerks. These are sudden accelerations in how the field changes, moments when the normally gradual drift becomes a sharp pivot. The most recent major jerk occurred in 2016, and it was so pronounced that researchers had to update the world magnetic model ahead of schedule. This is the mathematical framework that everything from smartphone compasses to military navigation systems relies on. When the planet's magnetic behavior outpaces our models, we are forced to acknowledge just how dynamic this system really is. Now, let's address the question that's probably forming in your mind. Are we heading toward another magnetic reversal? Are we witnessing the early stages of something like the Laschamp Excursion? The honest answer is that we simply don't know, and that uncertainty tells us something important about the limits of prediction when dealing with planetary-scale phenomena. Computer models suggest that a full reversal could still be thousands of years away, or it could begin within centuries. The magnetic field's current weakening trend could reverse itself tomorrow, or it could accelerate. What we do know is that the signs we're seeing today bear some resemblance to what geological records suggest happened before previous reversals. The weakening field, the accelerating pole movement, the magnetic jerks, these are all features that scientists have identified in the geological fingerprints of past magnetic transitions. But here's where our modern situation becomes uniquely complicated. The Neanderthals and early humans who lived through the Laschamp Excursion didn't have GPS satellites orbiting overhead. They didn't have power grids stretching across continents or communication networks that depend on radio waves bouncing predictably off the ionosphere. Our technological civilization has built itself on the assumption of magnetic stability. Every satellite in orbit, every transcontinental flight, every credit card transaction that relies on precise timing signals, all of this infrastructure assumes that Earth's magnetic field will behave more or less as it has for the past few centuries. What would happen if that assumption proved false? If we experienced even a minor magnetic excursion, not a full reversal but just a significant weakening and reorganization of the field? The immediate effects wouldn't be catastrophic, but they would be pervasive. Satellite operations would become increasingly difficult as radiation exposure increased. The beautiful auroras that normally stay confined to polar regions would begin appearing at lower latitudes, but their beauty would come with a cost. The same particles creating those displays would be disrupting radio communications and degrading solar panels. Airlines would face new challenges as radiation levels increased on polar routes, potentially forcing them to reroute flights and limit crew exposure. Power grids, especially those spanning large distances, would become more vulnerable to geomagnetically induced currents, the same phenomenon that caused the 1989 Quebec blackout but potentially on a much larger scale. Perhaps most concerning would be the gradual degradation of our GPS constellation. These satellites already struggle with radiation damage from solar storms, but in a weakened magnetic field, that damage would accumulate much faster. And once you start losing GPS precision, the ripple effect spread through every system that depends on accurate positioning and timing data. There's an irony here that isn't lost on researchers studying magnetic reversals. The same technological sophistication that makes us vulnerable to magnetic field changes also gives us unprecedented ability to monitor and understand those changes. We have satellites measuring the field strength in real time, ground-based observatories tracking its variations, and computer models that can simulate its behavior with increasing accuracy. This knowledge is what allows us to prepare. Understanding the Laschamp Excursion isn't just an exercise in paleontology, it's a preview of what our interconnected world might face. The ancient magnetic chaos that our predecessors survived without even knowing it was happening could profoundly disrupt the delicate web of systems we depend on. But here's what the geological record also tells us, and this is perhaps the most important lesson from our journey through deep time. Earth's magnetic field has weakened before, wandered before, even disappeared almost entirely before, and it has always recovered. The Laschamp Excursion lasted less than 1,000 years, and then the field strengthened and stabilized. Our planet's magnetic dynamo is resilient in ways that operate on timescales far longer than human civilization has existed. While we worry about the next century or millennium, Earth measures magnetic time in hundreds of thousands of years, confident in its ability to regenerate the shield that protects all life. Still, as we track magnetic north sprint toward Siberia and watch our field strength decline, we're reminded that we live on a dynamic planet whose invisible protective systems are far from permanent. And so we find ourselves dancing with forces that dwarf human comprehension, caught in a cosmic ballet that's been playing out for billions of years. The Laschamp Excursion, for all its ancient drama, offers us a mirror to understand our present predicament. We live in an age where our technology has become exquisitely sensitive to the very magnetic forces our ancestors weathered with nothing but stone tools and cave paintings. You might be wondering how something that happened 42,000 years ago connects to your smartphone losing GPS signal or your laptop mysteriously rebooting during a solar storm. The answer lies in understanding that Earth's magnetic field isn't just a historical curiosity, it's an active, breathing system that continues to shape our daily lives in ways we're only beginning to appreciate. Consider what happened in March 1989. A relatively minor magnetic storm, nothing compared to the chaos of the Laschamp Excursion, knocked out power across Quebec, leaving 6 million people without electricity for 9 hours. The storm induced electrical currents in the long-distance power lines, overwhelming transformers and cascading through the grid like dominoes falling. What struck engineers wasn't just the blackout itself, but how vulnerable our modern infrastructure had become to the same cosmic forces that once painted auroras across Stone Age skies. We've built a civilization that depends entirely on systems our ancestors couldn't have imagined, yet these systems are remarkably fragile when cosmic weather turns rough. Satellites wobble in their orbits when magnetic storms heat and expand the upper atmosphere, creating unexpected drag. GPS signals scatter and bend as charged particles flood through the ionosphere. Airlines reroute polar flights to avoid radiation exposure that can damage both electronics and human tissue. Each of these disruptions echoes, in miniature, the planet-wide chaos that defined the Laschamp millennium. But here's where the story gets particularly fascinating. We're not just passive victims of magnetic turbulence, we've become active participants in this cosmic dance. Every time we launch a satellite, we're placing a delicate piece of technology directly into the path of the solar wind. Every undersea cable we lay, every power grid we expand, every wireless network we deploy, we're creating new pathways for magnetic storms to follow. In a sense, we've woven ourselves so deeply into Earth's electromagnetic environment that we can no longer separate human technology from planetary magnetism. The International Space Station experiences this intimately. Orbiting at the edge of our magnetosphere's protection, the station and its crew receive radiation doses that would be unthinkable at sea level. During major solar storms, astronauts retreat to the most shielded compartments, waiting out cosmic weather that would have been just another night of spectacular auroras for our Paleolithic ancestors. The same magnetic chaos that may have inspired the first cave paintings now threatens to corrupt the computer systems keeping humans alive in space. You can see this vulnerability playing out in smaller ways too. Ham radio operators know to expect strange propagation during magnetic storms, as the ionosphere churns and shifts like an invisible ocean above our heads. Miners working underground sometimes lose contact with surface operations when magnetic disturbances interfere with communication systems. Even something as mundane as electronic car keys can malfunction during particularly intense space weather events. What makes this modern predicament so intriguing is how it connects us to the deep history of our planet. The same magnetic instabilities that may have pushed Neanderthals toward extinction now have the power to ground commercial aircraft and shut down stock exchanges. The cosmic rays that once bombarded unprotected cave painters are still streaming toward Earth, held back only by the same invisible shield that weakened so catastrophically during the Laschamp Excursion. We're living through what scientists call the space age, but we're doing so while Earth's magnetic field continues its ancient pattern of wandering and weakening. Magnetic north has moved more in the past 20 years than in the previous century, racing across the Arctic at speeds that force frequent updates to navigation systems worldwide. Commercial ships find their compasses pointing increasingly off-true, while airport runways must be renumbered as magnetic declination shifts beyond acceptable margins. The question that keeps geophysicists up at night isn't whether another magnetic excursion will happen, it's whether our technology-dependent civilization will be ready when it does. Unlike the small bands of hunter-gatherers who survived the Laschamp chaos with spears and fire, we've created a global network of interdependent systems that could cascade into failure if cosmic weather turns truly severe. A magnetic storm 10 times stronger than the 1989 Quebec event could potentially disable power grids across entire continents, leaving billions without electricity for weeks or months. Yet there's something oddly comforting about this cosmic vulnerability. It reminds us that despite all our technological sophistication, we remain citizens of a dynamic planet orbiting a variable star in a galaxy filled with energetic phenomena beyond our control. The same magnetic forces that create the northern lights still shape our daily lives, connecting us to processes that began billions of years ago and will continue long after our species has moved on. In a way, we're experiencing the Laschamp Excursion in slow motion, spread across centuries rather than compressed into a single dramatic millennium. Our magnetic field continues to weaken, our poles continue to wander, and we continue to build technologies that make us ever more sensitive to the cosmic forces our planet has always navigated. The difference is that now we can measure these changes, predict their consequences, and perhaps even prepare for them. The solar wind that once painted Stone Age skies with impossible colors still streams past our planet every day, held back by the same magnetic shield that faltered so dramatically 42,000 years ago. When we look up at the occasional aurora dancing across northern skies, we're witnessing the same fundamental interaction between Earth and space that has shaped the conditions for life throughout geological time. We're all participants in this ancient cosmic dance, whether we're aware of it or not. And so we come to perhaps the most remarkable part of this story. The shield returns. After nearly 1,000 years of magnetic chaos, after watching the invisible guardian that protects our world weaken to just 6% of its normal strength, after enduring cosmic radiation storms and atmospheric devastation that fundamentally altered the conditions for life on Earth, something extraordinary happened. The magnetic field began to heal itself. This wasn't a sudden switch, like flipping a light back on after a power outage. The recovery was gradual, measured in centuries rather than decades. Deep within Earth's outer core, the churning ocean of liquid iron that generates our magnetic field slowly found its rhythm again. The convection patterns that had been disrupted, the electric currents that had weakened and wandered, began to reorganize themselves into the stable configuration we know today. You might wonder how we know this recovery happened, given that 42,000 years is a long time to track magnetic behavior. The answer lies in the same geological archives that first revealed the Laschamp Excursion to us. Those volcanic rocks, those lake sediments, those buried trees, they all continued recording the magnetic field signature as it strengthened. Scientists can read this recovery like chapters in a book, watching the magnetic intensity climb year by year, century by century, until Earth's protective shield was fully restored. What's fascinating is that the field didn't just snap back to its previous state. It rebuilt itself into something slightly different, the way a broken bone heals stronger at the fracture point. The magnetic poles settled into positions that were close to, but not identical to, where they'd been before the excursion began. It's as if our planet learned something from its ordeal, adapting its magnetic architecture in subtle ways that reflect the trauma and recovery of that extraordinary millennium. And life? Life did what it does best. It adapted, it survived, it flourished once again. The Neanderthals who had watched those spectacular auroras dancing across equatorial skies were gone by the time the magnetic field fully recovered, but their genetic legacy lived on in the human populations that had learned to navigate this transformed world. Modern humans, our direct ancestors, had weathered one of the most challenging periods in recent planetary history and emerged not just intact, but arguably stronger and more adaptable than before. This recovery offers us something profound to consider as we lie here in the darkness. Earth's magnetic field has collapsed before, and it has rebuilt itself before. Our planet has faced cosmic storms that make today's space weather look gentle by comparison, and yet here we are. The biosphere has endured radiation levels that would sterilize modern technology, and yet life continued. There's a resilience built into the very structure of our world that operates on timescales so vast they're difficult for us to fully comprehend. When scientists today study the weakening of our current magnetic field, when they track the rapid movement of magnetic north across the Arctic, they don't do so from a place of panic. They do so with the knowledge that our planet has been through this before. The Laschamp Excursion isn't just a cautionary tale about vulnerability, it's also a story about recovery. It's evidence that the systems that sustain life on Earth are more robust, more self-correcting, than we might imagine. This doesn't mean we should be complacent about our technological vulnerability, of course. Our satellites and power grids exist in a very different context than the stone tools and cave paintings of 42,000 years ago. But it does mean we can approach the future with something other than fear. We can approach it with the curiosity and wonder that brought us to this story in the first place. The invisible fortress that surrounds us right now, deflecting solar winds and cosmic rays as you listen to these words, is the product of that ancient recovery. Every breath you take, every moment of peaceful sleep you're about to enjoy, exists within the protective embrace of a magnetic field that has proven its ability to heal itself. The aurora that occasionally graces our northern skies is no longer a sign of planetary crisis, but rather a gentle reminder of the cosmic dance that continues around us, held in check by forces we're only beginning to understand. As we reach the end of our journey back to the Laschamp Excursion, we find ourselves in a curious position. We began by looking backward through deep time, tracing the story of a planet whose magnetic shield had failed. We followed cosmic radiation as it poured through a compromised magnetosphere, watched climate systems reorganize themselves, witnessed the final chapters of Neanderthal existence unfold against skies painted with unprecedented auroral displays. But here, at the story's end, we discover we've also been looking forward. The magnetic field that recovered from the Laschamp Excursion, that rebuilt itself over centuries of patient reconstruction, is the same field that protects us now. The resilience our planet demonstrated 42,000 years ago is the same resilience that operates today. We are not separate from this story, we are its continuation. In a few hours, the sun will rise over a world still held safe within its magnetic cocoon. Charged particles from our star will encounter Earth's invisible boundary and be gently deflected away, continuing their journey into the outer solar system just as they have for millions of years. The same fundamental processes that allowed life to survive the Laschamp Excursion continue to operate with quiet efficiency, requiring no acknowledgement or appreciation from us to do their work. So as you settle into sleep, you can rest knowing that you're cradled not just in the gravity of a stable planet, but within the protective embrace of a magnetic field that has proven its capacity for both crisis and recovery. The story of the Laschamp Excursion reminds us that resilience operates on scales both vast and intimate, from the churning of liquid iron deep beneath our feet to the quiet rhythm of your breathing in the darkness. The shield has returned, stronger and wiser for its ancient ordeal. And under its protection, we dream forward into tomorrow.